You tell?
Now we're live.
Okay, we are live. Hello, everybody. Welcome to MIT and Salt Lake City. So I'm Chris, and my colleague upstairs in the same building as me, Simone, just below me, and then Greg in Salt Lake City. Hi. So today we're going to be talking about a ocean model called Oceananigans.jl, and this is work with a whole bunch of people today. We've got myself, Greg, and Simone presenting, and we've also got a bunch of people on the kind of Q&A, monitoring responses. Francis, Tomas, Suyash, Rodrigo, and Jean-Michel, probably. We're not sure exactly who's there, but someone is there. And the goal of today is really to look inside this ocean model. I'm just getting a message that says we're having trouble streaming to Twitch. So I'm just going to ignore that message.
Sorry, Twitch users.
Yeah, sorry, Twitch users.
Sorry.
And the goal of this session is really to dissect. So who remembers, I don't know which of you out there dissected frogs in school, but we're going to dissect our ocean model. So that's what this little cartoon on the right here is showing.
Frogs in school anymore. That sounds crazy.
Is that right? Okay, I don't know. I'm so old.
Well, I don't know. Did you do that? Wow.
Okay, so let's.
A lot of frogs sacrificed in the name of science. Oceananigans, no animals were harmed in the.
Exactly, Oceananigans doesn't harm frogs. Okay, so the workshop goals are some hands-on experience with Oceananigans as an ocean model. We're going to show some illustrative numerical examples, the ticker on the bottom of the screen, and you can also ask on Pigeonhole if you can't find where to go, but the ticker on the bottom of the screen shows where the code examples are and also has a link to the actual raw code of Oceananigans. So we're hoping that people will, as we talk, will also be looking at the code, getting a bit familiar. But we're going to work through
more examples there.
Yeah, we're going to work through two long examples to show you how things sort of fit together. These are all things that you can run yourself in Julia 1.6. They mostly run in 1.7, except apparently on M1 Max, there's some issues with 1.7. The examples can run in the REPL or in notebooks, and you can also run them in Google Colab. And there's a link on the slides that, and you can ask about that link in Pigeonhole as well, because I'm just realizing you can't click on that link. That shows you in Colab, you have to add a little bit of extra Julia, but Colab lets you actually just run some stuff, in the cloud for free. And we'll show you that GPUs are faster than CPUs for some of the modeling stuff we do. So after the hands-on stuff, we're going to look at some of the inner workings of the code. So we're going to try and show how we're using Julia to express our ocean model, some of the abstractions we found really nice in the Julia language to support the sort of numerical and computational workflows we have around sort of finite volume fluid dynamics. And then if there's time, we're going to try and fit in a learning parameters example where actually, there's no point in having a model these days if you can't train it automatically. We don't want to do all that parameter tuning ourselves by hand anymore. So we might try and get to showing how to automate finding the optimum parameters for a particular ocean model problem. So roughly, we're going to spend about 15 minutes kind of just introducing ocean modeling. Then about an hour, we'll see how it goes on the simulation examples. We have two of them. One is a non-hydrostatic idealized process model. The other is a planetary scale ocean model. Then about another hour or so in some code dive and looking at the language and how we use it. And then depending on time, getting to the learning example. And then towards the end, we'll have just general discussion through Pigeonhole if we can. As we go, we're going to leap to Pigeonhole periodically to check questions and try and answer them. So feel free to throw questions in there.
And we've already got one question.
There you go. We'll have a look in a second. So
I tried to answer it.
Okay, good. But yeah, Pigeonhole is the way to interact with us as we talk. We are Julia 6 for this session. And at least for me, all the tools we have work well in Chrome, not always quite as well in Firefox and Safari. So if you don't have Chrome, maybe you need to install that at some point. And yeah, go to live.julia.con.org, obviously, to see the live stream. You wouldn't know that if you weren't watching the live stream. So you probably know that already. Okay, let's go and just check out what's happening in Pigeonhole before we delve in. Okay. How can I view the output of the first model in the repo? So the first model in the repo is, I forget.
I think if you're talking about the JuliaCon 2022 repo, then, and if by output you mean the plot. Uh-oh.
Yep.
Can you hear me? If my
yeah, we can hear you. Yep.
Okay, yeah. Then I think typing display fig will display the figure on your screen, if that's what's being referred to. The data is saved in a .jld2 file, but anyways.
So that's if you're running in the REPL, yeah, you kind of do that, yeah. Is that you're saying, Greg?
True. Yeah. Yeah, I don't know. Maybe there's a different example that's being referred to. I'm not sure.
Yeah, if it's the GP Ocean example, then there's no output at the moment. So I'm going to go through that later, and I'll show you.
Okay.
Okay. So let's go back. So with that, and we'll come back to Pigeonhole kind of every 10, 15 minutes. Let's go on to Greg. Do you want to do this from your screen?
Sure.
So I'll put you to the stream there. Okay.
Nice. Awesome.
Okay.
Okay. Yeah. So I'm let's see. Okay. Yeah. So I'm gonna present about just a basic overview of what Oceananigans is and what it's intended to do. And I should have put Schmidt futures down at the bottom, but we have Klima there, so maybe that covers it. And this might be 15 minutes, might be shorter. So first, for those of you who are Julia enthusiasts, but maybe not ocean enthusiasts, I just want to, it's called Oceananigans. So obviously it has something to do with the ocean. And so I think it's worthwhile to spend a couple minutes explaining what we mean by that. So we're physicists. So when we talk about the ocean, we're talking about we're talking about the physics of the ocean. So Oceananigans is concerned with the ocean, the fluid dynamics. So for us, the ocean is a fluid. It's a salty, variable temperature fluid, which means that gravitational forces, density differences in density are important for the fluid dynamics. And it's in a complex domain. So, we have continents, we have seamounts, we have rough bathymetry. So those are the kinds of things that are important to us. And I guess it's also worth mentioning that obviously the Earth is a sphere. So the ocean is in a thin spherical shell on the surface of the Earth. But that's an important use case for Oceananigans. But we're also interested in idealized problems that where processes might occur in things like rectangles, for example. The scales of interest in physical oceanography, just writ broadly, range from you could say they are actually smaller than hundreds of meters, but I'll just say that Oceananigans it's a sort of designed to treat problems that the smallest scales are around meters to hundreds of meters, and the largest problems span the whole Earth, so thousands of kilometers. And what Oceananigans is, getting more into the details, it's a code that solves partial differential equations that model the fluid dynamics of the ocean. So it's a physical model for the Earth's ocean. And we don't specialize in other aspects of oceanography like chemistry or biology, but we do support coupling the core models for the physics of the ocean with models for chemistry and biology. Okay, so that's my introduction to what the ocean is. Now, Oceananigans is a Julia library that, as I said, we use to model the ocean. And I'm calling it a library deliberately for people who are, for Julia enthusiasts, all packages are libraries, basically. So this is nothing all that interesting. But I think it's worth commenting that as a historical note that many ocean models in the past were sort of, they weren't written as libraries. They're written more as these black boxes or boxes of varying transparencies that the way that you interact with it is that you give it a text file, like some kind of input file or name list, and it outputs data. But what we've tried to do with Oceananigans, like oftentimes you use it that way, but we've tried to design it so that the steps that lead to the running of the ocean model are more exposed, so that people can be more creative with the experiments they're running, and they have more control over the numerical experiments that they build. So users of Oceananigans are now Julia programmers rather than people who are just configuring name lists and text files. Oceananigans is designed for both small and large scale oceanography, which is another unique feature of, or somewhat unique feature. There's other models out there that do this too, but many don't. So many codes are designed either for large scale or for small scale. What that means for us is that we have models that can solve non-hydrostatic equations, and we have models that can solve the hydrostatic equations. We might get more into what that means specifically, but we can do large-eddy simulation, but we can also do global circulation modeling. So the primary purpose of Oceananigans is to couple with the other components in an Earth system model being developed by the Climate Modeling Alliance, or CLIMA. And what our purpose there is to do data-driven Earth system modeling, or a more systematic estimation of pre-parameters that show up in Earth system models. Our second vision, which we're trying to piggyback, so we're funded to develop this Earth system model, but we're developing it in Julia, so we think that we can also achieve another vision, which is to greatly accelerate and enable innovative computational oceanography, which is part of what I was saying before, by building a library where people have more control over their numerical experiments. And this is JuliaCon, so it's worth mentioning that we leverage a wide range of packages in the Julia ecosystem, from kernel abstractions to support CPU or GPU execution, CUDA.jl, support hopefully coming soon for AMD as well, AMD GPUs, JLD2, NetCDF, MPI, Pencil FFTs, Makie for visualization, and many more packages that I'm not mentioning. So Oceananigans is really it's a Julia library. Okay, so just to showcase some examples. So to get more into the details, we use kernel abstractions, as I mentioned, to support multi-threaded execution on the CPU and GPU execution using the same underlying code for both cases. So that's an important feature of Oceananigans. We don't write the model isn't written. Models aren't written twice, one for CPU, one for GPU. We have prototype support for multi-GPU execution in a single process using some CUDA features, and also prototype support for multi-node execution. So that's distributed memory using MPI. But both of those are sort of works in progress, and if you want to help out, please do. So the first example I'm showing, I should play these again, is an example in a rectangular domain. It's periodic in one direction, the direction that the flow is going in, and bounded in the other two. And it's a simulation of turbulence driven by the wind and surface waves at a laboratory scale. And the bottom example is a hole, or it's a simulation on the sphere, so a global ocean simulation at a 1/4 degree resolution, which at that resolution you resolve part of what we call the mesoscale eddy field, which are all the interesting wiggles and eddies visible in that visualization. Okay, so I think that's it. Yeah. Okay, so that's it for the background. So any questions on Pigeonhole? Probably should give people a little bit of time to
Yeah, so should we go to the pigeonhole thing and just see? There are a few questions that...
oh, yeah. Yeah, open it up.
So let's go there. So, so are models designed to be more deterministic, since you mentioned data-driven models? I think the answer is they're designed to maybe be more authentically accurate to the real world, but the fluid dynamics is still slightly chaotic, and so determinism, there's certain things that are deterministic, some large-scale behaviors we think, but there's also a lot of interesting turbulence in these things. That means they have a stochastic side to them as well. So yes and no, I guess.
Well, right. I would say they're no more deterministic than other ocean models, right?
Yeah, I think the data-driven part is trying to make them fit the real world more accurately at some point. We're trying to come up with more, but they're still the level of determinism kind of is built into the fluid dynamics.
It's a hard question because there's like an emergent stochasticity. That's what Chris is talking about. And there's also the possibility that you introduce explicit stochasticity into the model. But I would say in general, though, it's not designed to be any more or less deterministic than existing ocean models. That's not
Yeah. So to answer the first question, as you asked about the resources, I think both of the simulation are run on one GPU.
Yeah.
So, it's a V100. So we can actually fit quite complex models on one GPU.
So the movie Greg showed, which was
I think both simulations were actually run on Titan 5.
Yeah, Titan 5.
Yeah.
But we do also run on V100s.
Yeah. But the movie on the sphere that you showed, Greg, I think that's on a 4 V100, isn't it? It's kind of about that.
No, that's on a single Titan 5.
Yeah.
Okay. I thought, that was not the 12th. We do have one that we're running on.
We have one of the simulation that runs on 4 different V100s, which is a little bit more resolved.
Yeah.
But at a quarter of a degree, you can go on just one Titan 5.
So we don't. Almost everybody using Oceananigans, if you're using it for research or practical applications, you're typically running on a single GPU.
Yeah.
And we're working on, we have this prototype support for multi-GPU, which will support even larger problems, some of the really big ones.
Yeah.
Okay, how about this? Is there something in the formulation that makes Oceananigans not suitable for atmospheric fluids? Maybe radiation.
Yeah, it's radiation, and we're solving for incompressible flow at the moment. So if you wanna, we had some plans, I think, to put in a compressible model, but it's not really available yet.
So let me. So later on in the presentation, we're going to get into the internals of Oceananigans, and what we'll describe is that Oceananigans is it's actually this sort of sprawling code right now, and it includes one part of it is a engine for finite volume calculations. Another part are utilities for running experiments, and then on top of those, we've implemented models for physics. So Oceananigans has 3 physics models: a shallow water model, a non-hydrostatic model, and a hydrostatic model. And so the models are responsible for implementing, the specific equations being solved. So it's just the case that right now we don't have any equation set that would be, you can use like a Boolean-esque non-hydrostatic approximation, as Simone was mentioning, incompressible approximation for some atmospheric problems, but for like a global atmosphere, you need a slightly different equation set, and we don't have that implemented right now. But there's nothing if formulation is sort of vague, but if you're talking about the code structure, there's nothing in the code structure that prevents you from writing a new model for the atmosphere. Yeah, and radiation is not an issue.
The underlying engine would work also for atmosphere.
Yeah. So I think we should stick with going through a few questions before we go back. Does that sound good to you, Greg and Simone?
Yeah, I think this is the most useful thing.
Yeah. But yeah, we will get to showing some code as well, because that's so practical industry uses. I think Oceananigans is kind of grown up in a research universe first and foremost. Certainly, it has a target for climate predictability and prediction and trying to reduce uncertainty in climate forecasts that people will use for, planning large investments out to 30 years or longer. It is based on an algorithm, or a lot of it's based on an algorithm we call the MIT General Circulation Model, MIT GCM. That has been around longer and is actually used kind of in environmental studies quite often these days. So it's used both for research, but also, and Oceananigans could go the same way. So some examples of that are, people use this form of this larger kind of pre-existing code for looking at environmental impacts of desalination plants. There's interesting work looking at sea level rise around places like Nantucket. So there are some kind of environmental organizations that use these algorithms, not too many using Julia quite yet. Those are using slightly older versions of the same algorithm.
Right. So basically ocean modeling, there's a lot of industrial applications of ocean modeling in general, but nobody's using Oceananigans yet for those.
We've only been, Oceananigans is about 2 years old, so it's a new kid on the block at the moment. So,
also the applications are increasing. Climate change is becoming more. People are worrying about it more and trying to do more about it, and the ocean is a fundamental component of the Earth system. So those applications are increasing.
Okay,
I can try to answer this acoustic question.
Yeah, go for it.
Mm-hmm. I think I just tried to look up what bellhop was. It's like a ray tracing code, I think. So I would say that something like that is probably outside the scope of the Oceananigans package itself. But what Oceananigans would provide is a temperature field, or a structure, ocean structure. The output of Oceananigans would be used as an input into a code like bellhop. But we're primarily interested in modeling the fluid dynamics, like the velocities and stuff like that. So no plans to do acoustic modeling.
But people have used, as Greg says, again, in the MIT GCM world, which is kind of the same algorithm, they've used solutions from that model for a lot of interesting acoustic work. There's some, so the 1/12 of a degree simulation that Simone shows on a sphere, I think in his example, which is the one I think that does run on 4 GPUs. There's a similar MIT GCM run we did to that, where people did some fascinating work looking at something called the Heard Island experiment, and the resolution was such that you could actually see. So the Heard Island experiment was a 1960s acoustic experiment where people let off a loud acoustic source in the Indian Ocean, and then you could detect it at Bermuda and things. And explaining exactly the travel time and where those acoustic signals were heard has always been an interesting problem that people study globally, because they turn up with a certain time and that tells you about the state of the ocean and things. So right. That sort of global model actually is kind of fun for doing that, and there are people who do that sort of stuff. So okay, we'll do one more question, shall we? Searching for probabilistic search for finding vessels lost at sea. Anyone want to try? Any comments on that?
That well, not right now. Only because, well, mainly because we're still like putting together like a realistic. We're on our way towards realistic simulations, but we're not on our way towards like a forecasting level type of simulation. So that's some time out. But I think people do use ocean models for, Of course, I don't know if they. I was reading about the Indian Ocean plane crash. I don't think they. I think people were pretty surprised actually where the debris ended up being.
Yeah, people tried to explain it using circulation models, and I think it wasn't that successful sometimes. They were left with.
Yeah.
But when there have been big oil spills and things, people do, oil is kind of a mix of a kind of fluid and parcels of blobs of messy stuff, and people certainly use models like this for looking at, where to go to kind of clean up oil spills and try and block them and things like that. So,
yeah, you could envision that being an application a few years down the line, but definitely not right now.
Okay, let's go to let's do a bit of code, shall we?
Yep.
I think that's next on the list. So now we have hands-on code along, and I think you're on again, Greg, because you kind of had you scheduled in.
Really on the hook, yeah.
Yeah. So do you want to share from your screen? Is that?
Yeah. Okay. So
the font's pretty small there.
Oh, let me get it. Yeah, let's increase it. Okay, so the intention of this part is, so what I'm going to do is I'm going to walk everyone through the process of writing so me and Simone are both going to walk people through the process of writing a numerical experiment that simulates something relevant to the ocean. My example is a simple sort of classroom level example of that illustrates the process of convection. Actually, I had a slide. Maybe I should go back to I had a slide. So my example illustrates the process of convection, and Simone's example is going to illustrate. So mine will be non-hydrostatic. I'm going to do it on the CPU, and Simone's example is going to be hydrostatic simulation on the sphere on a GPU. And I think we figured out all the stuff you needed to do to get that to work. 15 minutes. Okay, so I'm going to go fast. Okay, so my example's a simple convection example. And I guess if you'd like to start, I should have put the code here. So let me, if you'd like to look at the code while I'm talking, this is not going to work. Give me a second. I'll find the link. So here's our repo. So the code I'm going to present is in this Oceananigans.jl script. Okay, so if you'd like to, this is what I'm going to code up the script like line by line. But if you'd like to see what we're aiming towards at the end, you can look at this. Okay, so just for those of you who don't know, convection, so people define convection different ways. When we say convection, we're talking about gravity-driven flow due to density gradients. And a typical example is density gradients associated with temperature. So for example, if you heat a pan on the stove, you're heating it from below, and hot fluid is light, so the hot fluid wants to rise, and that process produces turbulent convection. It's a fundamental process in the ocean and the atmosphere. And in this example, I'm going to write a script that models convection in just 2 dimensions. That's going to make the problem a little cheaper computationally. And because vertical accelerations are important in convection, I'm going to use Oceananigans' non-hydrostatic model for this problem. Okay, so let's see where we're. Okay, so here's the repo again. And so the script is here, ocean convection. I'm going to start a new file and attempt to reproduce this. So we'll see. Yeah, let me get this as a reference. Okay, so ocean convection demo. So I don't know, this is JuliaCon. So many people may be familiar with Julia's package manager, but in case you're not, the way to install Oceananigans is to open up Julia. So I've already done that. I ran the script to precompile everything, so this goes a little faster. And you type add Oceananigans. Oceananigans is a registered package in the Julia general registry, so that should find it and install it. Sometimes there's issues with versioning if you have other packages in your environment, but that's the basic process. And I've already done that here, so I'm not going to press enter there. Okay, now when we're writing a script, the first thing we have to do is we have to say using Oceananigans. So I'm going to write that. And then the next, let me just a second. Okay, and then the next step is to is to So we're trying to model convection in a two-dimensional domain. So the first thing to do is we have to build a grid that divides the domain of interest into small boxes. That's in Oceananigans using a finite volume method. So building the grid is the first fundamental step in building a numerical experiment. So in this case, I'm going to use the rectilinear grid, which is for problems in rectangles. So this can represent domains that are 1, 2, or 3-dimensional, which each dimension orthogonal to the other. And I'm going to use a modest. So I'm going to do a 2-dimensional grid, and I'm going to use a modest size, 64 squared. And this will run hopefully pretty quickly on my Mac. We call the 3 dimensions are called X, Y, Z. So I'm gonna design this experiment to be an X and Z. And I'm going to make X go from 0 to 128. The units are not specified, but let's say we're using meters here. And so this is, this will be 2-meter grid spacing in the horizontal. And as is customary in the ocean, we put 0 at the surface. So the Z direction is going to go from -64 to 0. And finally, I'm going to specify what we call a topology. So this the topology defines the nature of the directions. So in this case, my X direction is going to be periodic. My Y direction, I don't have a Y direction, so I'm gonna label that flat, which means that means that it's dropping out of the problem, and the problem is only 2-dimensional. And I'm going to say the Z direction is bounded, which means that I have solid walls at the top and the bottom. Okay, so let's run this. Okay, so it ran quickly and produced a grid. And Chris has asked me to, Chris, you can jump in if you asked me to illustrate the help functionality.
Yes, go for it.
I built the grid.
Somebody's asking on Pigeonhole, you can increase the font a bit as well. I don't know. I think just
yeah. Okay.
I was answering some other questions, but I just noticed that one. But yeah, well, Greg does that. But there are, for all of the functions, there's some nice help. So yeah, if you show that, that'd be kind of fun to see as well. You can just
So okay, so here you can see I call the object grid, and you can see it's created here 64 by 1, which is the Y direction by 64. Periodic in X, bounded in Z. If we want to know anything else that we might pass to rectilinear grid, we can use the help. So if we type question mark and then rectilinear grid, we get this very long help string. That gives you all sorts of other information. Maybe one key thing to note is that implicitly, I didn't specify the architecture. So it's the default is CPU, but if you want to run on the GPU, then you change the first argument here, GPU, like that. My Mac doesn't have a GPU, so I'm not going to do that. Okay. Okay, so we've got a grid, and now the next thing to build is a model. So we're going to build a non-hydrostatic model on the grid that we've built. And let's run this again. It takes a little bit of time because it's allocating memory for all the fields in the model. Okay, so we've built a model. We've got a non-hydrostatic model on a rectilinear grid. It's using this particular time-stepping method. Adam Bash, second order, quasi second order Adams Bashforth method. It has no tracers, which are the fields that are advected by the velocity field. No turbulence closure, no buoyancy, and no Coriolis. So the fact that we don't have any tracers or buoyancy means that we're not going to be able to model convection with this model. So, or I should use another word besides model. We're not going to be able to simulate convection with this model. So the next thing to do is to add tracers to the model. And what I'm going to do here is I'm going to use a tracer that represents the value of the tracer. It's analogous to temperature, but it's called buoyancy. So I'm going to call it B. And I'm going to use a buoyancy model that the buoyant acceleration incurred in the fluid is proportional to the value of buoyancy. So to do that, I write this buoyancy tracer. Run this again. It's readable. Okay. So now we're going to rebuild the model. And you can see now we have a tracer called B, and the buoyancy model is the buoyancy tracer, and gravity is pointing in the -z direction. Okay, so that's the typical experience on Earth where gravity points down. Okay, so what does it mean to have a field? So now this model has tracers, a tracer called B, and what that means is that it's allocated memory for a field that's going to represent buoyancy. And that memory, okay, let's see. So that memory is wrapped in an object that we call a field with capital F. And you can see that we have a little summary of the values of the field down here. And it's 0 everywhere. So the first thing to do is to change. So what I want to model an initial value problem in which the buoyancy is unstable initially, and then which causes convection. So to do that, I'm going to have to change the values of buoyancy. So for that, I write. Okay, so let's see. I'm going to the first thing I'm going to try is I'm going to make buoyancy. I'm going to make this variable called epsilon function epsilon, which is normally distributed random variable, and I'm just going to set buoyancy equal to epsilon. So if you rerun this, and look again, okay, so now we see that writing set. So what set does is that it changes the values of a field, and then this is a convenience function that changes all the values of any field in the model all at the same time. So here I wrote set model with buoyancy equal to this function. And so it evaluated that function on every grid point. And as a result, we have a buoyancy field that has a small, the mean should, if we had enough resolution, it would be closer to 0, I guess. But you can see it has some maximum and minimum values here. So it's randomly distributed. And then okay, let's see. So I haven't done any visualization yet. So it's useful to look at the buoyancy field to see what it looks like. So let's create a visualization. I'm just going to use Makie for that. Heat map. So let's see if we can see what that does. Display, like I was saying. Okay, so cool. So so far we've created a model. It has a buoyancy tracer, which represents buoyant acceleration applied to the fluid, and we were able to change the distribution of buoyancy to be randomly random. And so this is what the buoyancy looks like in our 64 by 64 domain. Okay, so now I'm going to do something slightly less trivial. I'm going to make it an unstable distribution. So just give me a moment. I have less time to explain exactly what I'm doing here, but I'll try to. So what I'm going to do is I'm going to make a buoyancy distribution that's hot on the bottom and cold on the top, kind of similar to the situation that would occur, at least transiently, in the pan that you heated up on the stove. And I'm just going to make it a tanh function so that it has a smooth distribution for that. So let's see. I'm gonna put it, so I want to make it so that it transitions from hot to cold in the middle of the domain and has a width of 4 meters. So that's what that means. And then I'm going to reduce the amplitude of the noise compared to this buoyancy perturbation. Okay. So let's see. So that's the initial buoyancy distribution I like to use. So let's see if we can. Works. Nice. Okay, cool. Yeah. Okay, so there's no color bar, but anyways, yellow is warm and blue is cold, luckily. Yeah, so it's tanh. You can see it doesn't depend on X except for the randomness, the small. You can kind of see the random noise a little bit. You might think it's dirt on your screen, but there's a little bit of randomness. That helps to kick the instability off. We need a little bit of randomness for that. Yeah, it looks good. Actually, I think we're ready to try to run this. I think at least preliminarily, preliminary simulation of this scenario. So let's do that. Okay, so in order to, I have a model that represents the physical problem I'd like to solve, but the next thing I have to do is I'm going to build a simulation which will step this model forward in time and potentially do some other things that might be important for my scientific problem, like saving output to disk or maybe logging something to the screen so I know what's going on in the simulation. And so for that, I'm going to use Oceananigans simulation object with a capital S, which requires me to give it a time step. So I'm just going to guess what the time step might need to be, and I'll run it for 1,000 iterations. Okay, let's see what happens. Okay, so the way the script is structured now, I set the buoyancy field to this tanh, I build a simulation, and then I plot what the buoyancy is after I run it. So let's do that. It might take a little bit more time to run. Hopefully not too much time. Okay, now it's running. I think it's running, but I'm not. It's kind of just sitting there. So one thing that's pretty useful. Okay, so it was doing the initial time step. Yeah. One thing that's useful actually is to print. Let's look at the results for you. Oh, it's doing something. Nice. It's starting to convect, I think. So one thing that's useful, is one thing while simulation is running, especially if it's a long-running simulation, we typically want to print something to the screen that tells us what the progress of the simulation is. And so we can do that using this feature called a callback. So that's the first thing. I'll just illustrate how we would do that with Oceananigans simulation. So going to callback is basically a function that runs at a specified schedule. So here, the function is just going to print something to the screen. Let's say it's going to print the model iteration and the time. And I'm sort of pretending to use physical units, so I'll use this function pretty time, which will tell me that it's seconds or minutes or whatever. Okay, so and then I want to add this as a callback. I'll print it every 10 iterations. Let's run it. Maybe for 2,000. Maybe something more is going to happen if we run it a little longer. Okay, let's see how that works. Oops, I have an error. Oh. So callbacks. Yeah, so this callbacks property is a ordered dictionary to which we add all the callbacks. Okay. Nice. Okay, so now it's running, it's executing that callback every 10 iterations, and we have some more faith that the simulation is actually running and it's not paused. Okay. Ooh. Okay, it ran longer, but if you look closely, you'll notice that there's a lot of variation grid point to grid point in this output. Now, if you're a computational scientist, you might understand immediately what's going on. But for those of you who don't, I'll just explain that we set up this model, and maybe it's worth showing that the model is associated with an advection scheme here, but it's a centered second-order advection scheme, which is a low-order, non-dissipative advection scheme. So we have little or no numerical dissipation in the problem and no explicit dissipation, or no diffusivity or viscosity. And so as a result, the simulation is pretty noisy, non-physical. Real fluids have dissipation. So to better model this problem, I'm going to have to add some dissipation. And I think I'd also like to use a higher order advection scheme, which will produce higher quality results as well. So I'm going to add a new advection scheme called we know. That's the best advection scheme we have right now. And let's also I'm also going to add a turbulence closure. So I'm going to add a isotropic constant viscosity and diffusivity using the turbulence closure scalar diffusivity. And since I cheated and ran this problem a lot in advance, I know that 0.1 is a good value to choose for this domain. In this case, so my domain is 128 meters by 64 meters. So this diffusivity is actually a turbulence closure. It's a model for turbulence that's occurring below the scale of the grid. This is not the molecular diffusivity, but if you wanted to, you could attempt to use a diffusivity that corresponds to the molecular diffusivity of the fluid, in which case you would be doing what's called direct numerical simulation. But here we're not doing that. We're doing an idealized model of the problem. Okay, so let's run it again. Okay, so we're using Wino. It's going to might take some time to, oh, not too much time. Okay, it's running. Takes a little bit longer. As models get more complicated, they get more and more expensive, especially with the higher order advection scheme, but not too much time. Okay. Oh, it doesn't look so bad though. Cool. All right. Yeah. So someone clapped. Was that you? Yeah, good. Chris is clapping. Yeah, Chris is excited. All right. So let's see. I'm probably over my 15 minutes. So I think to wrap this up, and you can, if you look at the script on the repo, you'll see a bunch of other things I included in the script. Like, oh, let's do two more things. Okay, two more things. I'm gonna save some output to disk, and then I'm gonna make an animation. Those are the two things I think that are important. Okay, so far all I did was I ran a simulation and I plotted the field at the end. But typically we're interested in more than just what the distribution is at the end of the simulation. We want to know its time history. So to inspect that, we save output to disk. And to save output to disk, we use Oceananigans output writers. So I'll show you what that looks like briefly. Okay, so if I want to, so let's see. I just want to have my cheat sheet here ready. Okay. So we're going to add an output writer to this. I'll call it JLD2 because we're going to use the JLD2 output writer. And the first argument to the output writer is a model. The second argument is a named tuple of fields that represent the output. So in this, I'm going to do two outputs. The first output I'm going to do is just the buoyancy field itself. So I'll show you. So that's if I wanted to output the buoyancy field, I just create a named tuple and I'm going to call it B. That's what it's called inside the model. And then the next thing I give to it is a schedule. So this is going to tell me, this is saying when I'd like to output, and let's run it for 4,000, and I'll output, what should I do? If I do every 400, it'll be 10. I'll do every 200 iterations. So iteration 200. I also need to give it a file name. So I'm going to call it convection.jld2. And we often include this flag overwrite existing, which means if there's an existing file, just overwrite it. That doesn't matter the first time I run it, but subsequent times there's going to be existing data and I want to delete it every time I go. Okay, so I added an output writer, and okay, so everything's okay. So let's just run it again and see. Actually, just for this first thing, when I make the movie, I'll run it for. Let's just make it a little bit cheaper so this goes faster. So I just want to show that this, if we build this, did I? Okay, I said override existing equals false. True is what we want. True. Okay, let's run it again. Okay, so yeah, we have a JLD2 file in here, but it actually may have been created by a different simulation. So I'm going to remove that. Again, okay. I knew that was happening because that warning that was flashing on the screen. Okay, so now, so I ran it again, and it created this JLD2 file here. And we could look into it, but let's not, just for the sake of time. Suffice to say that it has data, and if we trust that everything worked correctly, the data is has a buoyancy field in it, a time series of the buoyancy field saved every 200 iterations. So that's how you build output with Oceananigans. Now, one of Oceananigans' most interesting features is its ability to save output that consists of not arbitrary, but complicated calculus and arithmetic operations applied to the model fields. So, and why is that? So, for example, one interesting thing that we might want to compute is the vorticity of the fluid, which quantifies the rate at which each fluid parcel is rotating. So the vorticity requires taking derivatives of the velocity field. So in Oceananigans, I'm going to call it xz. And so let me show you this we'll have a little thing on the on this feature later on in the thing, but I'll just give a little introduction to it. So if I want to define an object that represents vorticity, I write it, and I always get the sign wrong, so the actual vorticity might be minus this thing, but in any case, so I have three fields that represent the velocity components, and to create an object that represents vorticity, I write this expression that looks very similar to the way you would write it with pencil, the d by dx of u minus d by dz of w, and that creates this object called an operation, which is a lazy representation of the computation of vorticity. So showed you how to create an operation. So what we're going to do is we're going to put xz here, and we're going to say that we want to save not just b, but also xz. So that's how you. So this illustrates how you can schedule output that it not just consists of fields, but also computations performed on fields. And you can also, you can slice them. So, if you have a 3D simulation, you typically don't want to output 3D data every time step. And you can also average them in time before outputting them. So I'm not going to, before I run this again, let's create a visualization. So I'll expand this simple thing into, so to create a visualization, what I have to do is I have to load the data. You can load the data several ways. Some people prefer to visualize in Python. Some people save with NetCDF for that purpose. I think you can also look at JLD2 data in Python. But what I like to do, I like to use Julia, and Oceananigans includes this nice feature useful for analysis called field time series. So I'm going to construct a field time series that's a time series of the data that was saved in my file. So the first argument is Oceananigans.jl2, and then the second argument is the name of the field that the time series consists of. And now I'm going to do some Makie stuff that I don't know. I don't know how many people are Makie aficionados, but what I'm going to do is, let's see, I'm going to create two panels in my figure. And then I'm going to use this, let's see, two panels. Then I'm going to do a slider. I'm going to create a slider so we can explore the data after we create it. And then I'm going to use this function called lift. That's very magical. That allows me to visualize the evolving data. So I don't need that. It should be enough. Okay, so let's run it again. Oh, let's run it for the 4,000 that we wanted to do. So this works. Let's say if I made a typo or not somewhere. I'll find out. 4,000. Yeah, it takes some
Right.
time. Oh, we don't have to run it again after this, so.
Mm-hmm.
Okay, there's a problem. What happened? That's kind of unexpected. So that there's 21 values.
Oh, Greg, what's going on?
Well, now I'm not sure. Things look pretty good.
Don't you know observable for that?
Let's have a look.
Oh, that's what happened. Thanks, Simone. That's what I meant to write. Okay, yeah. And here I'll just, I won't run the simulation again.
Yeah.
But sharp eyes. Yeah, so I had this n variable, but it was being taken from something else. Not the right thing. Okay, so here. Okay, great. Great. Okay, so yeah, so it did it. Yep, and you can see there's some convection. Let's see. Pretty coarse, but you know, that's life. That's life on StreamYard.
There you go.
Yeah, so right. So here we go. So we were visualizing, so you know,
beautiful. Very, very
our initial condition, the top panel's buoyancy, the bottom panel's vorticity. As we step it forward, we start off, everything starts off as random noise, but then we see this instability develop. I believe this is called Rayleigh-Taylor instability. Is that right?
Yeah.
So the hot fluid's rising into the cold fluid. It's associated with a vorticity signal. And then we get some eddies and things swirl around and start mixing. So
yeah, next time you put a saucepan on your stove, this is what's going on, yeah?
More or less. Same physics, anyways. If you really wanted to model the pan, you have to use a boundary condition with a heat flux, which you could also do in Oceananigans, but I didn't illustrate that. But yeah, so you know, the GitHub script it shows you how to make an animation with color bars and save it as a movie, etc. But this is the basic part. Okay.
So there were a couple of YouTube questions as well, because people can ask questions, I think, or they can ask questions on the stream. So yeah. So one was just what's a tracer? Do you want to try and explain what you meant by tracer, just so that?
Yeah. So there's two types of fields. I mean, in the non-hydrostatic model, there's two types of fields. One is the velocity field, which we represent through 3 velocity components, and that that's like quantifying the motion of the fluid. A tracer is a quantity that's carried by the fluid. So temperature, heat is a tracer. So you know, if you have a current moving, then it carries its temperature with it. Salinity is a tracer, and you know, other chemical species are tracers. So hopefully that explains it.
Yeah. Yep. And then, okay, should we go and look at Pigeonhole briefly? I think.
Sure. Someone said, "Can we stick a rigid structure in? Would that be a boundary? Is that on this? Is that? I don't know if that's Oceananigans or not. Because all the sessions are concatenated into one StreamYard comment thing. So
I think that's about immersed boundaries. So I'm going to show.
So Simone is going to show how to put continents in here. So that's kind of like a rigid structure. So we'll see that next.
Very complex geometry.
Let's see if we can. Did that put us into? Yeah. So the StreamYard ones. I think people have been answering them behind the scenes, but maybe, I don't know, if you set topology, periodic, flat periodic on a rectilinear grid, would that be like an ocean on a torus? Kind of, yeah, I think. Typically, you do periodic, flat more than periodic, flat, periodic. That's kind of the last dimension, which is we call Z, is usually our vertical dimension, which we kind of don't think of very often.
Topologically, it is a torus.
Yeah.
But on an actual torus, its surface is curved, so that changes things a little bit. So here it's like, that's what it means to be periodic. Yeah, that's one way to think about it.
And then there's what kind of, so I think Argel you were asking, I think this question in particular was asking about we know. I'll just go and look inside, I think, because I answered a bit, but Simone, do you want to say a tiny bit about we know and diffusion? Because as Greg was looking at centered second order.
Yeah. So with our we know scheme, we actually have inbuilt diffusion. So we don't need to add some explicit diffusivity, because we know should actually take care. It calculates the reconstruction dynamically based on the field. So it allows you to run without a diffusivity that you would put in for stability. So our code is stable without an explicit diffusivity in the shallow water model specifically. So we don't need to have an additional diffusivity. But we have some models so we need some closures to represent what happens at smaller scales. So we have closures for viscosity, not for diffusivity at the moment. So we have some closures to express how velocity, how turbulence mixes velocity or momentum at scales that are smaller than the grid.
Okay, let's do one more, which was, what does hydrostatic mean? Maybe just either Greg or Simone, you could say a little bit about the difference between kind of large scale and small scale models. So Greg was looking at a non-hydrostatic thing, and Simone is going to look at hydrostatic. Do you want to?
Yeah, so the hydrostatic approximation, that's what we mean by that, it's when it's referring to pressure. So when pressure is hydrostatic, it means that it's determined by a static or quasi-static balance between, in the Oceananigans case, it's between the vertical pressure gradient, the Z pressure gradient, and the buoyancy field. So in a hydrostatic model, that balance dominates the vertical momentum equation, and there's no vertical acceleration, whereas in a non-hydrostatic model, we explicitly model vertical accelerations. So the hydrostatic model is appropriate for fluids that have very small aspect ratios, like the ocean. So the horizontal scale is much larger than the vertical scale. So that's like basically the.
Nice, yeah. And then there's one last question, I guess. So we just touch on all of them. What's special about the first time step? Why does it take very long compared with the other time steps? And that's kind of answered in line here, but
usually, it's about the compilation. So the Julia has to go through all the functions that we use on precompiling the first time. So that takes a lot of extra time.
But then after that, we do thousands of time steps normally in a real simulation. So you amortize that cost over a large number of time steps. Okay, you're filling up to showing a global thing, Simone.
I'm going to try to show an ocean now.
Yeah.
Let's see.
That's what everybody's been waiting for. So,
should I share it? Wait a second. Let me.
We can. I think. Are you sharing?
Should I share? Maybe.
Yeah, I can do it for you. I just did it. I think. There you go.
Is the size large enough?
Pretty small to me, but let me.
If you need a bigger font. But so I'm gonna try to do like Greg here, and now give you all the steps to actually build an ocean model with Oceananigans. So I'll give all the ingredients that we need, and see if in the end we actually have something that resembles a real ocean. It's not gonna be the most fantastical resolved ocean, because this is the resource we have here. But let's see where we can get. So I have the code here on GitHub. It's GPU Ocean SimOcean.jl if you want to follow it. But I'm gonna try to code live. And for who doesn't have a GPU, I have this instruction at the beginning that tells you to run on a GPU. And if you don't have it and you want to code along, you just have to change this line to CPU, and everything will work properly on your CPU. So if you want to try it, you can do that. Okay, so let's see where we can get. Let's do oceandemo.jl. So using Oceananigans and using GLMax. Let's go like this. So first of all, we need a grid to simulate the ocean, but this time rectilinear grid is not enough. It's not, because we need to discretize a sphere. So Oceananigans for this has a latitude longitude grid. Probably have to look there. Grid. And this grid will have, instead of having the Cartesian x and y direction, we'll have the longitude direction on the x and the latitude direction on the y. So let's start giving it a size. The modest size here, not huge. Then we have to specify a longitude, and in this case, we want to give it the degrees of the grid, or longitude of the grid, and we go from minus 180 and 180 degrees. So this grid will wrap around the whole Earth. Then we have to give it a latitude span, and this grid is it discretized latitude and longitude. So when you go to the poles, the longitude circles actually collapse into a singularity. So we cannot give it from minus 90 to 90, but we have to stay away from the poles. And we do this by specifying, by just falling off a little bit short from the poles. In this case, I give it like minus 84 to 84 degrees. And the specific numbers are because I run this problem and have boundary conditions that are set on this exact grid. And then we need a z direction. Let's give it an ocean depth. In this case, we start with a depth of 3.6 kilometers, which is kind of realistic. And give it a z direction. Let's say this file. Okay, so I hope, okay, I have pre-compiled everything. So now we have latitude longitude grids that will run on a CPU, and it spans from minus 180 to 180 degrees with a grid spacing of 2.8 degrees in the longitude and latitude direction, and with 300 meters in the vertical direction. So the first thing that we can do to improve this grid is we don't have so many grid points. We actually have only 12 points in the vertical direction. So what we can do is, since in the ocean everything really happens at the surface and not much happens at the bottom, we can actually stretch the grid towards the surface. So we can make better use of our vertical levels. So let's start actually giving some parameters here to make it a little bit easier to work it around. 12. So to make a grid on Oceananigans stretched in one direction, you can pass it either an array or a function of the index. In this case, I've already defined a function which works, but you can define whatever kind of function. It just has to be monotonic with the index, so you can have a stretch grid. Let's see. So let's define a sigma, and this how do I define it? I'll define it as z times sigma 1 times divided by z. So sorry, this should be a k. So in this case, this grid will grid spacing will have a spacing which will depend on the index, and should decrease as you increase the decay. Wait a second. I'm a little bit.
How's it going? Let's have a look.
A second here. So this should be correct. And then we have to define.
You could always run it and see what it looks like. Yes. Oh, you have to. I see. You have to get the z coordinate from the delta z, right?
Yeah.
But that's in the grid. Yeah, you can get that out of the grid. Nice.
This, and then we can define traces. Which will be so if k is our first point, then
that's the bottom.
That will be the bottom of the grid. Minus LZ. Otherwise, we'll have M minus LZ plus the sum of the previous delta Z. Sorry, a second. I have to remember a bit this function. Okay, so here we go. This should work. So now we have defined
typo minus LZ, not underscore. Right there. Yeah. Nice.
Okay, so this should give us a function that has phases that go from minus LZ to 0 in increasing order. Let's see how it looks like.
Oh, I get to save it.
Yes. Yeah. Okay. And then I have to pass the function to the grid, of course. Okay, now, so if you compare this grid with this one, you'll see that here we have a Z which goes from minus 3.6 kilometers to 0 again, but it's variably spaced. So it has a delta Z that goes from 124 near the top to 577 meters near the bottom. Now, as was mentioned before, for an ocean we also need bathymetry. So we need to give it the continents and the bottom of the ocean. And for this one, I actually have given a file, a JLD2 file that you can load in. I think it's called
bathymetry _ JuliaCon.
Julia. Okay. On the JLD2, if I'm not mistaken, the name of this is bathymetry. Okay. Let's call it bathymetry. So this is what our bathymetry looks like. It's just an array of an X and Y size, which will tell to our grid. Let me make it a little bit smaller. That will tell to our grid what is the actual bottom of our ocean. So if we overlay this one to this array to our grid.
So when I make that bigger, yeah, there you go.
Okay. If we overlay this array to our grid, the grid will know that whatever is above it will be part of the fluid domain, and whatever is below it will actually be part of a continent or will be covered by terrain. So everything will be massed to 0 and not be calculated. As you can see, this bathymetry is kind of coarse, but it has everything that we need. So it has Africa here, the America, some bottom here, some ridges. So to overlay this to our grid, we have the immerse grid type. So let's call this underlying grid, maybe underlying grid. And we can immerse this with our immerse boundary grid. So this type, yeah. In this way, we'll know that we'll take this grid, and this grid will know that whatever is below the bathymetry array will be covered from the computation. Save it. Okay, so this grid is actually an immersed boundary grid, which has a bottom that goes from -6 kilometers to 0. So 0 is going to be where our continents are, and this is going to be the most deep part of the ocean, which we actually don't touch because our grid only goes to -3.6 kilometers. So now we define the grid, and the next part is to define our physics, the physics of our problem. So to define our physics, we first need to, we have several parts that we have to define. One of the first one is the Coriolis Force. So the Earth is actually rotating. The Earth is rotating. So we have to express this in our model. We have several ways to express the Coriolis Force. So you can be on a plane, or you can be on a small patch of the Earth. But in this case, we want to have a way to represent the whole sphere. So we have a type which is called hydrostatic spherical Coriolis, which we can give a rotation rate. In this case, let's put rotation rate of 1, and then we'll have our model will know that our sphere is spinning with a 1 degree a radian per second. Of course, this is a little bit too high for Earth, so we can take this away, and we'll get automatically by default the rotation rate of the Earth, which in this case is in the order of 1 to the -e at the -5, 1 10 to the -5. The second part of the physics that we have to specify is our buoyancy. And Greg used a buoyancy tracer, but here we have a method to specify that we actually have the buoyancy depends on temperature and salinity. And in this case, we can specify seawater buoyancy, and this means that our buoyancy will depend on a temperature through a thermal expansion coefficient, and to a salinity through a Halline contraction coefficient. So we have to remember when we specify the model that we have to pass in temperature and salinity tracers, because there will be need for buoyancy calculation. Again, we can as Greg said before, we have to specify a diffusivity, because we need a way to model everything that happens under in subgrid scales. So we need a way to represent what the mixing that happens within one grid cell, and we do this through a diffusivity, an artificial diffusivity and artificial viscosity. We need to do this in a vertical direction and in the horizontal direction, but our grid is very anisotropic, because the vertical direction, if you see the grid, our vertical direction has a spacing of about 100 meters, while our horizontal direction has a spacing of about 3 degrees of a circle of the whole Earth, and that results in roughly 300 kilometers. So our grid cell is 300 kilometers wide and about 100 meters tall. So our diffusivity, much more can happen in the horizontal direction than in the vertical direction. So for this reason, we need a much higher diffusivity in the horizontal than in the vertical direction. So for horizontal diffusivity, we can specify horizontal scalar diffusivity with viscosity. We have to keep it quite large here because, as I said, there are 300 kilometers that we have to cover. So 1 to the power 5, it's a good value, and the diffusivity of 1 to the power 2 is also a good value here. In the vertical direction, on the other hand, since our vertical scales are much smaller, we need a much smaller diffusivity. Scalar diffusivity, and that is about, we can use 1 and 20 to the minus 3, and I already know this because I run this already. But they scale roughly with the grid size. And another thing that we can specify for the vertical diffusivity is that since our heights are very small, we will probably be limited in time stepping if we just run it like this, because the diffusion will happen very fast. So we need to have a time step that represent that diffusion. So in this case, we can actually specify, give it as an argument, vertically implicit time discretization. So this will tell our model that specifically this closure over here, discretization, will not be stepped in time explicitly, but will be stepped in time implicitly. And to do that, Chris is going to say later how solvers work, but we have to solve a tree-diagonal system. And in this way, we're not limited in the time step. Again, we're going to use a hydrostatic model, so that's going to be different from what Greg showed. And we have no way to represent convection, because convection can happen only in a non-hydrostatic model. So exactly what Greg was showing of having a hot fluid below a cold fluid could not happen in our simulation. So we need a way to express the mixing without having a vertical velocity, and we do that with a model which targets the mixing when this situation happens. So exactly when you have something light that is below something heavy. And in oceanography, we call this convective adjustment because it's just a way to represent convection where we cannot represent convection. Adjustment. And we have several models for this, but the most simple, it's just a vertical diffusivity. It's just a vertical diffusivity that that happens when you have an unstable fluid situation. Just diffusivity, and we have to specify convective diffusivity that we keep a little bit higher than what we have in our background diffusivity. So these are all the closures that we'll need for our model. We don't need anything else. We need our horizontal diffusivity, vertical diffusivity, convective adjustment. Okay. Let's hope this runs. No, convective adjustment is physical. Convective adjustment, vertical. How was it specified? The typing error. Convective KZ, yeah. So this is a vertical diffusivity, so we have to specify convective KZ, not only a convective K. Okay, so we have our closures, which are horizontal, vertical diffusivity, and convective adjustment. We have our Coriolis Force, which is values in latitude, and we have our buoyancy model. Now, another thing that we need to specify are boundary conditions. Because at the moment, our ocean is still, nothing is happening. So we need to add some forcing somewhere. And our ocean will have a u velocity, so there's a velocity along the longitude, a v velocity along the latitude, a temperature, and a salinity. So we need to specify boundary conditions for these quantities. Now, I already have prepared some boundary conditions for this problem, and you can look at them in the file boundary condition JuliaCon, so I can include them. Boundary conditions JLDO. JLD2. Okay, so these boundary conditions are actually 2D arrays, are 2D arrays of size nx and y, because they represent what happens at the surface of the ocean. So at the surface of the ocean, you have winds, and winds push your velocity field, and are represented by these tau x and tau y terms, which are stress, are the stress that the wind imposes on the surface of the ocean. And then we have also a surface temperature that we will use to as a boundary condition for the temperature field, and there's the effect of the sun heating the Earth at the equator, and the Earth losing heat through radiation or convection. I can show you a little bit how these arrays look like. So first of all, let's import them here. Let's call them tau x is our wind in the longitude direction. X, and we have tau y. Tau y is gonna be our wind in the y direction, and let's call it Ts, our surface temperature. Okay, so these are how these arrays look like. Just put it a little bit higher, otherwise I don't really see here. Okay. This is the wind. Stress in the longitudinal direction. So we have strong winds in the Southern Ocean pushing the flow eastward, and strong winds also in the North Atlantic, while in the equator we have winds pushing the other direction. You can see that winds here are a little bit coarse, but this is the resolution that we have. And you see that where the continents are, we don't really have any wind because we don't need it. This is the wind stress in the latitudinal direction. There's a little bit less discernible structure, but it for sure has some values. And then we have the surface temperature, which of course it's the ocean is hot near the equator, where the sun rays are perpendicular, and colder near the Arctic and the Antarctic. So how do we pass these boundary conditions to the model? First of all, we have 3 different boundary condition types. So we have value boundary conditions. This is your typical Dirichlet boundary condition. We have gradient boundary conditions, and this is this imposes a gradient, so it's your normal boundary condition. And we can impose a flux. So this is actually the boundary condition that we're interested in. The condition, because the stress imposed by the wind is actually a flux of momentum in the ocean. So we can specify the boundary condition for UMV as simply as doing this flux boundary condition and X. Something that I forgot to mention is that if we run this on a GPU, which we didn't specify yet, because we have to specify here arc GPU, which I forgot to do, and pass it, as Greg said, as an argument to the grid. If we run on a GPU, these arrays have to be defined on a GPU. So we have a utility for that in Oceananigans, which is just arc array of the architecture and the array in question. In this case, our tau x is nothing but a q-array. So arc array just moves copies your array from the CPU to the GPU, and the other way around if you specify here CPU. So it's just an utility, but we need this array on the GPU if we're going to run our model on the GPU. So now we have our U boundary condition, U top boundary condition, which is a flux boundary condition and has this array as the actual boundary. So whenever we're going to go in the model, it's going to pick up the ij location of this array and impose it as a flux to the surface. Do the same thing for the v velocity. And for the temperature, we could define a value boundary condition, because we could prescribe the value of the temperature to be equal to the surface temperature, and that will look something like this. So if we do this, we force the temperature at the surface to be equal to the prescribed temperature, but we don't really want to do this now, because then all the dynamics of the surface will not be represented, because we'll fix the temperature of the surface. What we want to do is to give a relaxation to the temperature. So we want the temperature to relax to the surface temperature that we prescribe, so that we can allow it to be modified at the surface. And to do this, we can prescribe a flux boundary condition. So we're actually forcing the temperature to a prescribed value, and we can pass a function to the boundary condition. So if we pass a function to the boundary condition, the function will be evaluated at the boundary and used as a flux forcing. So let's call it restoring temperature, and we can define here this function. Restoring t. And this function will give us and this function will give us as a return value the flux evaluated at the ij location that we require. So the signature of this function is the ij location at which you have to evaluate the flux. Grid, as basically all of our functions. A clock. This clock holds the time of the simulation and the iteration. So in case you want to have a boundary condition that changes with time, you have this information passing through this clock. And then we pass the fields. These fields are all the fields that the model holds. So in this case, U, V, T, and S, which are passed to the boundary condition, and some custom parameters that we want to pass to the function. In this case, we know what the surface temperature is, because it's passed through to the boundary condition through the model through this fields argument, and it's just the temperature, a location ij, and the k location is the top is the surface, so it's grid.nz, and our target temperature, the temperature we want to restore our surface temperature to, we're passing it through the parameters argument. There's going to be parameters dot t ij with ts. Now the flux that we want to evaluate is a restoring flux, so we can pass it through a restoring parameter. Let's call it lambda, and then our surface temperature minus our target temperature. This function, we can pass it directly to the flux boundary condition, and will be evaluated at each point at each time. We define it as giving it indices to the function. So we have two ways of defining boundary condition. We have continuous boundary functions, which depend on a position, and discrete boundary functions, which depend on indices. And in this case, since we have an array, we passed in indices, so we have to tell this to the boundary condition that this is a function in a discrete form. So tell it, and then we can pass the parameters of the function, which in this case are Ts, which is our surface temperature, and lambda, or restoring parameter, which we can put to 0.001. Okay, now we have all our surface boundary condition, and we have to put them into the boundary conditions of u, v, and t. And for this, we have a type called fields boundary condition. This type will contain all the boundary conditions of the field. So west, east, north, top, south, and bottom. South, north, south, top, and bottom, and immersed condition. And in this case, we want to change only a top boundary condition. This is what we specified. Top boundary condition. T, and same for T. Okay, let's run this. Field boundary conditions. Okay, so a field boundary condition will look something like this. So our U boundary conditions are default in all directions because we didn't specify anything. And we actually change the top boundary condition. This is going to be a flux that is specified by our coarray. And the same for our temperature. Everything is going to be a default. So a default means that in periodic direction, you're going to have periodic boundary conditions. And on walls, you're going to have zero flux. And we specified only a top boundary condition, which is a restoring function with parameters which are our surface temperature and our restoring parameter. So now we have everything that we need to specify our model. We define the physics, we define the boundary condition, we defined our grid, and we can construct our model. This is going to be a hydrostatic free surface model. So it's going to neglect the vertical direction. Because in the vertical direction, there's going to be only a balance between the pressure, force, and the buoyancy. We give it our grid. We give it our Coriolis, closures, boundary conditions, which are, let me just collect them here. They have to be a name tuple. Boundary conditions, and T is equal to T, boundary conditions. What am I missing? I'm missing the tracers and the buoyancy. So the buoyancy was specified. And the tracers, since we have a buoyancy that depends on temperature salinity, we have to specify temperature salinity as tracers. So in this case, we have a temperature tracer and a salinity tracer. And this is all we need to define an ocean. It doesn't take too much to precompile. We could also specify different advection schemes or different schemes for the free surface evolution, but that I kept everything for default. This is just the basics that we require to have an ocean up and running. Seems like it's taking a while to precompile. Okay, we have it. So this is our model, which runs on a GPU on an immersed boundary grid. It has a Adams-Bashford time stepper. So at the moment, we only implemented that for hydrostatic free surface model. We cannot use other time steppers. It has temperature and salinity tracers, and these are our three closures that we defined. The horizontal one, it's explicitly stepped, while the vertical ones are implicitly stepped. We have our buoyancy, and we are ready to run this model. So before that, we can set the model with some kind of realistic key initial conditions. So that means we set the temperature to something that can be the minimum temperature in our ocean, and our salinity to a realistic value. Okay. Let's save this first. Okay. And now we have a model. We can define a simulation. First of all, we need a time step. So the time step, a realistic time step in the ocean at this resolution is something like 20 minutes. And if I want to write here minutes, I have to use the fancy Oceananigans units module. Okay. So we run with a time step of 20 minutes, which is kind of realistic. And we run for 30 days. I can define our simulation. And let's hope that everything is specified correctly. And let's run it. Actually, no, let's put a progress first to show where we are. So this function is going to be a function that, as Greg showed, is going to be called in a callback to show our progress. So let's say time is going to be time observation model. The time is in the clock object. And let's print the maximum of the U velocity. So we tabbed on our simulation. Maximum of the absolute value of our simulation. Our U velocity is in velocities. U. And let's print also the maximum temperature. See how the temperature field adapts to our boundary conditions. Model.tracers, temperatures in the tracers object. Okay, now we can put this function in a callback. Let's give it an interval of the time steps, and let's run the simulation and see if nothing crashes. Oceananigans.
Mm-hmm. It's a tough thing to spell, yeah? It's always...
Yeah. Okay. See if it runs. I should have run it before, so
fingers crossed.
we compiled, but let's see if it takes too much time, if it has to recompile or not. Okay, initialize line. So we start with a zero velocity field everywhere because we didn't set the U velocity, and with a field which is -1 in temperature everywhere. Salinity, we actually give it a constant field and no boundary conditions, so we expect salinity to not change at all. While we expect temperature to increase at the surface and to match the boundary condition, and velocity to be pushed by the winds, especially in the Southern Ocean and in the Atlantic Ocean, where the winds were the strongest. Okay, initial time completed. So now it should be a little bit faster, hopefully. Okay, so our ocean is simulating. You can see that velocity temperature is adapting quite quickly to the boundary condition. The maximum of temperature is about 32 degrees, so it's adapting quite quickly. Our velocity is also reacting to the boundary condition, so that's nice to see. And the simulation is finished. So we just simulated 30 days of an ocean. We can look at the output now, what our model looks like. Look at first the temperature field. Here, model out. Let's look at the surface, which is the last point. I mean, it's 12 over here. Okay, so the temperature field has adapted quite nicely to the boundary condition. So we have a temperature which is quite higher at the equator and lower at the poles. But if we look at it in another plane, so let's now cut it in the Atlantic Ocean. So this would be around 80. That's how the interior of the ocean looks like. And we see that not much has happened in the actual interior. Everything happened near the surface at the moment. We probably have to run it for much more than 30 days to see something happening. We can also look at our velocity. Let's look at our U velocity, maybe. And the velocity field is being pushed around by the wind. So we have acceleration, eastward acceleration near the Southern Ocean and in the Atlantic, and westward near the Pacific Ocean. So that's kind of what we expected looking at the wind. There is quite some noise here near the Southern Ocean because we didn't really use very good numerical methods. So our direction, as Greg showed before, also our direction is all center second order. So we probably would need a Wino scheme to have this to have a better quality in our solutions. But yeah, this is basically the whole process of setting up a realistic ocean. And if you just throw resolution at it, you actually get very nice results. Because Chris, can I show the slides?
Yeah. Sorry, I just need to get back to this.
How do I show the slides?
Yeah, I'm just trying. Sorry, I had it on full screen. I'm just coming out of full screen and it's going slowly. I'll get there. So I think.
Chris, do you have the slides here?
I do. I can get
show the
yeah. So
the 112-degree ocean.
Yeah, I'll get that. Here we go.
Okay. So, if you look at that image, if you go to 112-degree below, yeah. So this ocean that you see here, this is a much more result than what I just did here. It's kind of it's 112-degree, so it's 40 times the resolution of what I have. But the methods are basically those. Nothing really changes much here. It's just use a slightly more sophisticated advection scheme. It runs on more GPUs, but all the methods that we put in the models are exactly the same. So it doesn't take much. Maybe like what was this 100 lines of code, and then you can have a kind of realistic ocean with Oceananigans.
Excellent. So I'm not sure we have many new questions in Pigeonhole.
And if you try this on the CPU, it's going to be a little bit slower, but it will run, and it will run in a decent time span.
So I'm just going to go to Pigeonhole, but I think everything is quiet there at the moment. I think people are just admiring the ocean.
Are there any questions on Pigeonhole?
So let's see. I'll just go through and just check whether there's any other ones that look the same. So
Greg disappeared.
We lost Greg. Hooray. So next up, we were actually going to start looking in some of the innards of the code. And so maybe we'll take, what do you think, Simone? Should we take like a 5-minute break just to
Yeah, I think so.
Pause for a bit?
How long will we be going?
We've been going an hour, yeah, 2 hours. So it's a good time for just a quick break. And
yeah.
Simone and I are in a building where the air conditioning isn't great, so it's kind of hot, at least in my office. You know, I need a glass of water. So maybe we'll take a 5-minute break and we'll come back. And because then Greg was also going to sort of give an overview of the code dive. So hopefully we'll get him back shortly. Otherwise, we can do it. Yeah?
Yeah, sure.
Okay. Let me see if I'll just... I'm going to see if I can put it. We are on a 5-minute break thing up. So on a 5-minute. Oh.
Oh, there you are.
Oh, Greg, you're back. So I said we'd just have a 5-minute break briefly to go and grab a glass of water or a coffee or anything like that.
That sounds good. Yeah, my computer just blinked. I don't know why that happened, but
okay. Yeah. So I'm just going to grab some water and stuff, and then we'll get into looking at the code. Hey, Simone, you back?
Yeah.
How's it going? Okay. So there is a question around how to estimate.
Where is it?
Kind of, I've got it on the screen. So is there a way to estimate upfront the resources needed for a given simulation?
So yeah, so the 1/4 of a degree model. So let's say that is
so that's 1440.
How much is it?
1440 by 720
into 48. So about a 40 million point grid fit on 12 gigabytes of memory. That's 600. 1440 times 600. Yeah. So that fits in on let's say 10 gigs. So of course, if you want to add diagnostics, so you want to add more fields, then you're gonna have to use more memory. You can have an estimate. So this 10 gigs are for the velocity fields and 2 for 5 fields. So let's say that one Oceananigans field on a 40 million grid point takes about 2 gigabytes. Yeah, a little bit less.
Also, you should clarify, the memory is allocated when we build the model, not when we build the simulation.
Yeah.
So,
yeah, the memory, all the fields are contained in the model.
So you typically, if you another way is through trial and error. I often use that. And you just build the model, and if it runs out of memory, then you're, you know what your situation is.
So for the realistic setup, how much does the immersed boundary take? Is it a 2D thing?
Yeah, it's a 2D thing. If you want to have more complex immersed boundaries, like something that
so there can be 3D immersed boundaries.
Yeah, then that will take a 3D memory field.
Yeah, but for the one you're doing,
wait, just so grid fitted bottom is 2D, grid fitted boundary is 3D. Most of the time, we're using 2D though.
Yeah.
Well, you don't need caves. Then you can use 2D.
You don't need caves or bridges.
Yeah.
Anyhow, okay. So yeah, so it's mostly those 5 3D fields. Yeah. I think.
Right. Well, it's 15, right? Because there's 2 tendency terms for each field.
Oh yeah. Okay. Now I have to edit my answer. I don't know how to do that.
Yeah, the footprint is it's roughly the number of prognostic fields times 3 plus the number of diagnostic fields, which can range from, I think, 1 to as many as there are tracers. So depends on the scenario being simulated. So some turbulence closures allocate a diagnostic field for every tracer. And you also have pressure.
Yeah, so Argel's asking a bit about some of the numerical methods. So for the hydrostatic case, I guess, Argel, there are some implicit solvers we use that involve, but they are kind of matrix free and they're actually 2D problems. For the non-hydrostatic stuff that Greg was showing,
there's either 1 or 2 scratch arrays.
Yeah, so that's yours was using an FFT based solver, was it, Greg? I forget.
Yeah, but that also uses 1 or 2 scratch arrays.
Yes, so that has a few scratch arrays for that.
So it's typically because of the complexity. We don't. I mean, I personally don't expend any effort trying to figure out, trying to calculate in advance. I mean, I don't know. There's no problem. Out of memory error is fine. So I usually do just trial and error personally, and then you get some sense for the particular setup you're doing, like what your boundary is.
Yeah. Okay. So we're 2 hours in, so I think we'll get through some of the code and probably won't get to the last bit we imagined. Yeah. So So I think next up is you, Greg. Do you want to share your screen, or do you just want me to page through the slides? Which do you want to?
I only have one slide for the overview, so how about you?
Okay, maybe I can just go to that. Yeah, should I do that?
You gonna do a slideshow or no?
If I do that, then it messes up my other stuff. So let's just do it this way. Sorry.
Okay, so this next section, we're going to dive, as they say, into the code. Although, as you can see, there's actually not a lot of code on this slide. So we're just going to try to describe the inner workings of Oceananigans and how the software, how the software is put together under the hood. So to start, I'm just going to give an overview of the structure of Oceananigans, and I've titled it Anatomy of an Ocean Model. So Oceananigans, the way I think about it is that it's essentially, it's kind of right now it's a mono repo for 3 distinct codes. And the 2 basic codes are the ones that are at the bottom of this pyramid. So the first one is an engine for discrete finite volume calculus on staggered grids. So that means that we're solving partial differential equations. So we need to have a way of representing things like derivatives and integrals. And so for that, we use a finite volume method. And then in addition to that, we're using this method, people call it a staggered grid method, where the location of some of the grids is staggered by half of a cell with respect to the others. And so if you don't know what that is, you probably want to read about it to learn more, because it can get sort of complicated under the hood. And so a lot of the features that we have are intended to help deal with doing calculations on a staggered grid. And so this engine, it involves some low-level features and some high-level features that the users see. So all the stuff that we kind of regard as user-facing is bolded on this slide. So some of the basic objects are the grids, rectilinear grid and latitude-longitude grid. Another basic object is the field object, which can represent 1, 2, or 3-dimensional fields. Either fields that either have data explicitly associated with them, memory associated with them, or a field can also represent a computation or a value without explicitly allocating the memory. Associated with fields is an infrastructure for building abstract operations, which that's a user-facing feature for constructing expression trees that represent calculations on the staggered grid. So derivatives, arithmetic, etc., and also reductions like averaging, maximum, minimum, etc. Chris, you have to go back to the slide.
Sorry.
Do you have a second screen or? No.
I'm sorry. Yeah.
No, it's okay.
I was responding to questions, but yeah.
Yeah, maybe I should be sharing.
That's fine. Carry on. I won't do it again. I just noticed there was a question.
For the next one, I'll share. Yeah, we'll get it up. Okay, so and then in addition to that the user-facing abstract operations, there's also a internal feature we call operators, which is a method for it plays the same role as abstract operations, but it's a little bit simpler and more performant and lower level. So it's another way to build expression trees that represent calculus computations, but at a lower level. And we use that to build kernels that can be executed on the GPU or CPU, representing computations like, for example, the right-hand side of a partial differential equation. And then finally, I'm also lumping into this finite volume engine the solvers that solve elliptic problems on Oceananigans grids, and sometimes the solvers have features that are specific to Oceananigans fields. So these solve, I mean, at the end of the day, in a discrete system, it boils down to solving linear algebra problems. Sometimes we use FFTs for that. Sometimes we use matrix-based methods, etc. Okay, so that's the engine for finite volume calculations. Now, there's another aspect of the code which has utilities for running numerical experiments. So basically, these are utilities for integrating a model forward in time. And in this context, I'm defining a model as it's a representation of the physics of the problem, and it also includes a time stepper. So these utilities for numerical experiments are really, they don't have any physics in them. They're just convenience functionality for running loops over a time stepping method with data that's with function callbacks and output writers, which intermittently write data to disk or execute some other task. I'm also lumping into this the field time series abstraction, which is a convenient feature for analyzing output, basically creating a time series of fields from data that's generated by an output writer. And then there's also a code-based interface with that. If you're writing a model, you have to define a couple of key functions, like a function that time steps the model forward, and a function that updates the diagnostic state of the model in order for the model to interface with the simulation. So those are the two. Think of those as the two building blocks that Oceananigans has implemented, and then the models, and right now we have three models: non-hydrostatic model, hydrostatic free surface model, and shallow water model. So those three models are implemented on top of those building blocks, leveraging the finite volume engine and interfacing with the simulation for user convenience. And so the models, what they do is they implement the numerical methods specific to certain physics. So like, for example, Coriolis forces involve a stencil that's specific to models that have Coriolis forces in them. And I'm also, including buoyancy models, turbulence closures, and forcing in that category. And so all the implementations of those types are in this model code. Models also implement physics-specific equation templates. So the way that an Oceananigans model typically works is that an equation with many terms is coded up into a kernel, and then the user toggles terms on and off, or controls their behavior with types like a type representing Coriolis forces or a type representing the turbulence closure. And finally, in Oceananigans, models also need to define a time-stepping method. So we've spent a little bit of effort in abstracting that, but I think the right way to think about it now is that every model has to implement its own time-stepping method, and that's because many of the time-stepping methods are specific to the physics problem being solved, and they include specific implicit, explicit treatments of different terms. Okay, so that's the basic anatomy of Oceananigans. And hopefully we'll have more models implemented in the Oceananigans infrastructure eventually. For example, CI's model.
Or a compressible in the future.
Or a compressible model, yeah.
So I'm just going to glance at the question. I think we probably covered them all, but let's go back just to see. I think that one's done with. Yeah. Okay. So I think next up, we're actually going to, for people who like to look at Julia code, start looking kind of under the hood a bit at what's actually in these layers that Greg described. So Simone, are you going to share? Are we going to add you?
No, leave the.
So yeah,
I can show this. So yeah, I'm going to talk a bit about the operators module. So this is kind of the backbone of our engine. It contains all the functions that we need to do derivatives, differences, also a little bit higher order operators such as Laplacian, higher order derivatives, second, third, and fourth. And this is all physics agnostic. So it all runs on a staggered grid. So the backbone of these operators is that we have our values defined at faces or centers. And these operators takes us from a center to a face, or vice versa. So for example, if you have your values defined at cells centers, you can derive it from the cell centers to a cell face. Or if you have it defined as cell faces, you can derive it from a cell face to a cell center. And you can do the same thing with interpolations. So these functions are actually very simple. I can show you a bit how probably it's better if I show it through here, because there's a bit of meta programming here that makes it slightly difficult. So can you go on with the slide?
Sure. Let me go. Do you want this?
Yeah, go there. There's a kind of example of how our operators are defined. If you go 2 slides after.
Yeah, I'm trying to. It's not moving for some reason. Hold on.
Okay. Anyways, these are
There you go.
These are very simple operations. They're all second order. So our differences here are second order, our interpolation are second order, our derivatives are second order. But they're designed in a certain way, which is kind of it is an example of how Oceananigans is designed. So they are, first of all, they're local. So each one of these operators take in a IJK index and are defined for a point in your grid. And they can be composable. So this is what I show here in this example. So we can have several ways to define a fourth order derivative, but the way in which it's done in Oceananigans is done through building blocks, or defining an abstract tree. So the most basic building block is a difference, and you can see how it's defined here at the top. A difference of a function is just the function evaluated. Let's say a difference in x is just the function evaluated at a certain point minus the function evaluated either at +1 or -1 in the x direction. And this is a very simple function, but we can use that to define a derivative. So a derivative in this case is defined as the difference divided by a spacing. And we can start composing functions in this way, right? So then the second derivative is going to be nothing but the derivative of the first derivative. So we can pass the derivative as an argument to the first derivative function, and this will give us a second derivative. And we can continue in this way to build up the third derivative. So the third derivative is nothing but the first derivative of a second derivative, which is a first derivative of a first derivative, and so on till the fourth derivative. And in this way, so for example, if you look at this fourth derivative stencil, right, it's defined at point ijk, but it's actually, if you follow through all the code, it actually takes in a 5-point stencil, because it's a difference of a difference of a difference of a difference. So in this way, we didn't really explicitly write a for loop over the stencil and summed the whole stencil, but we composed the function starting from very simple building blocks. And this is the way the whole of Oceananigans kind of works. Everything which is not global computation, for which we need actually solvers on this, Chris will talk about it later, is defined as a function of ijk, and if it can be constructed by simpler function, is always constructed as a trio of operations. So just to give an example, let's go to see a little bit of the code. I go back. So our tendency functions, which are quite complicated functions, are constructed in the same way. So we have, for example, if we look at the tendency functions, which calculate the whole divergence of the diffusive flux, the divergence of the advective flux. Function. Yeah. They are all pointwise operations. So this, for example, is the divergence of the advective flux, barotropic pressure gradient, the Coriolis force, the divergence of the diffusive field. They all depend on ijk grid. And if you look at what goes inside here, we're going to have a difference of fluxes. These fluxes will be defined as whatever closure you put into it, but they're always going to be defined pointwise, starting from basic operators. And this roughly how we specified we designed the whole code. And this has not only the advantage of the fact that the code actually it's a little bit simpler because it always starts from some simple basic blocks, which are the operators, but it also has the advantage that we can, in the end, we can wrap these local functions in kernels, which through the magic of kernel abstraction, which is a package I'm going to talk about later, abstracts all the loop over the grid. So we don't have to, usually codes have loops over IJK and then do the calculation, but we don't have that because we specify all our local functions and then we wrap it around this thing called kernel, and this kernel comes from a package kernel abstraction, and it's launched on a GPU or a CPU. Now, if it's launched on a GPU, the kernel will actually take the CUDA kernel structure, so it will launch it with a certain amount of threads and blocks, and will calculate the index and do the calculation locally individually for every CUDA core. And if you have a threaded system, the loop will be divided into the threads. If you have just one core, there's going to be a loop. But in this sense, we don't have a formal for loop. We only have local calculations that are wrapped around kernels. And this gives us simplicity in the code and hopefully performance. Yeah.
Great. Can I ask a question? Because
sure.
Nobody asked it. I thought somebody might ask it, but they haven't, so I'm going to ask it. So do you want to explain a tiny bit how we think about immersed boundaries in the regard of the operators like this and the magic of how that sort of happens as well? Just because, that's kind of clever too.
The immersed boundaries are, wait, let me just start up. Immersed boundaries actually extend all these operators. So if you have an immersed boundary, derivatives across immersed boundaries have to be 0. Interpolation have to take care that you have an immersed boundary there. So we extend all the operators. We probably will have a better way to do it soon, but where was it? Conditional fluxes and conditional derivatives. So all the operators, if they are specified on an immersed boundary, we'll see if the location of your grid is within or without an immersed boundary. If they are in a fluid domain, they will perform the operation that they have to perform. Otherwise, if we have an inactive node, then the operator will return a 0. That's just very simple way that we implement it. So there's an if condition that wraps around the operator.
Thanks. So let me go back to my screen.
Yeah.
So I think we were going to get.
Oh, gotta remove it. Yeah.
Oh, hold on. How do we do that?
Yeah. Okay. And to finish a bit, so this is not going to work. This whole wrapping around operators, local operators, will not work if we have a global computation. So that is the case if we have to solve an elliptic equation, and in that case, we have other techniques that we use. So we actually have some solvers that we implemented, and they will not follow this pattern. Also, for higher order, we have some higher order reconstructions that are specifically in the advection module. So the advection term, we do it with higher order methods, and in that case, we have to specify the whole reconstruction in one go. We cannot compose second order interpolations. So we have other operators which are specified specifically for advection in the advection module.
Okay. Greg, do you want me to show the abstract operation slides now, or
I can share.
Okay, go for it.
Okay, so in addition to that low-level interface for building expression trees, we also have a high-level interface for building expression trees that's user-facing that we call abstract operations. And I think you could think of this as it's a language for building lazy representations of these expression trees. So, and it supports reductions. So as an example, I'm showing you computing something that sort of resembles dissipation called epsilon. And so this epsilon is d by dx of u squared plus d by dy of v squared. And so I've created a graphical representation of what that looks on the right. So you can think of an expression tree as, nodes connected nodes, right? So plus is a binary operation that adds two binary operations, which themselves are power, which they take the derivative of u to the power 2 and add that to the derivative of y to the power 2. So that's what it looks like graphically. And so when we and it's sort of grayed out. Maybe see if it. Oh, okay. So oops. Okay, so I didn't have a. So this is what. So when you're using Oceananigans and you create this kind of object, this is what you get. You get a binary operation, and it has this sort of text art that represents the tree. And so this is potentially very powerful, although very complex operations sometimes don't compile on the GPU. But this is the system that we provide. So rather than so many other ocean models, they'll hard code certain diagnostics, and you select from a very long list which diagnostics you'd like to use. But our philosophy is slightly different. So instead of doing that, where we provide this language so that users can construct their own diagnostics. And so that's the importance of the abstract operations. And I guess if I could make a comment about the code, which was supposed to be the point of this section, I'd say that this is basically a re-implementation of Base's broadcasting. So it's very similar to how broadcasting works. It's all based around getIndex, extending getIndex for the different operations. And the wrinkle that we add is we have some infrastructure for doing these calculations on a staggered grid. So we make sure that things are all are sort of kosher and done correctly at the correct locations, given how the location of a field changes when you take its derivative, et cetera. And then the final comment that I wanted to make about abstract operations is, okay, oh yeah. So the other wrinkle with abstract operations is that, so in a simple case, like in this case with epsilon can be evaluated at ijk at any moment in time, and it uses the data that's currently in the field u and v. But in the case that an abstract operation, so to do that, we wrap the abstract operation in a field, so that allocates memory for it, and then we call compute on the field. In the case that some node in the abstract operation itself requires a global computation, so that would occur if the abstract operation depended on an average, for example, that means that we need to pre-compute that node if it hasn't been computed in order for the abstract operation to be correct. So the way that we do that is, so when we call compute on an abstract operation like epsilon, it goes through and recursively calls compute on every single node. And so in this case, we call compute on every node, but nothing happens because none of the nodes require any significant computation for this example. But if one of the nodes was something like an average or a maximum or a minimum or something like that, then that field would be computed prior to evaluating the abstract operation. So that's how this method works under the hood. And there's also a feature that attempts to, it's a sort of a small performance optimization that attempts to build some awareness of when a field was computed, so that if we evaluate many abstract operations that all depend on some average or global computation, that we don't end up recomputing that average if we don't need to. So we sort of like cache the the physical model time at which the computation is done, and check that before recomputing. So that's abstract operations.
Nice.
So did we want to have questions, or?
Yeah, I think there are a couple, so why don't we, I can bring up the, not sure they're directly related to abstract operations, but that's
okay.
One's about long wave simulations on like going up shores and things. Do you want to say something? You love that stuff, Greg. So.
Well, I don't know exactly what long wave run-up simulation is, but I guess we don't support wetting and drying, so I'm not sure if that matters. But in order to, if we wanted to have a simulation in which a wave, encroaches into previously dry land, we'd have to have a way of representing wetting and drying, or so Oceananigans can't do that, and we probably won't. Well, we might support some simple wetting and drying, but maybe not the extreme kind that would occur in that run-up scenario. I think that's more for a code that does like volume of fluid method or something like that.
When the other question, I think, is interesting. I guess, can you run more than one simulation in parallel while only having one GPU? So do you want to?
Yeah,
that's fine. We do run on a single GPU more than one simulation. I'm not extremely sure if that is recommended, because you're kind of stealing the resources from one simulation to another. So I know that modern GPUs have this feature of parallelizing the resources within the GPU itself. That's the A100 from NVIDIA, I think. But you would have to see how the GPU handles your simulation, because there's no feature specific.
We do it all the time.
Yeah, we do it all the time.
For CI.
Yeah.
Our CI runs, one of the machines we have has one GPU, and we run up to 16 jobs on that one GPU.
So. Yeah, but you would have to see and what kind of the resources your GPU has and how to utilize them.
Yeah. So there is also a feature in the code that I'm not sure we're going to get time to look at, which is the one you use for kind of ensemble runs, Greg, where you can actually run a bunch of independent columns in a single model, which is kind of like running lots and lots of different simulations in parallel, all within one configuration.
Right. Yeah. So if you have a problem that requires an ensemble of model runs, and every member of the ensemble is similar, and every member of the ensemble has one reduced dimension, then we do have some special features that are designed to support that case, which are utilized by this other package called parameter estimation.
And if we get time at the end, we might get to that. We'll see. Yeah, might just fit in a tiny bit. Okay, so I was going to talk a tiny bit about solvers next. So solvers, as we described them earlier, are the things we use for non-local computation. So everything we've looked at so far is mostly local stencils, although Greg mentioned averages and things, which obviously extend and so on. But there are places where we need to solve sets of equations that kind of go across many grid points. So that's what this solver layer in the kind of organization of the code is about. And in the ocean context, and just in the kind of fluid problems we've looked at so far, two places where we're doing this are shown here. So we've written solvers that are fairly general, but they're driven by what we need them for. So one is for mixing in the vertical, so along a single column, kind of handling a diffusion equation where the diffusion gets very large and we don't want to take a tiny time step. And one is for solving a 2D or 3D pressure equation, which is a place where in the Navier-Stokes equations, when you solve them numerically, there are some pressure terms that evolve in time that have very fast waves relative to all the other dynamics in the ocean. And we care more, or in many situations, we care more about their kind of average behavior than their instantaneous behavior. And so we have the option to kind of solve with a much bigger time step by using an implicit method for those. As it says here, the solvers are mostly generic numerical implementations that could apply to other domains as well. They're not really tied to the ocean. And some solvers also use external libraries like QFFT or FFTW. The set that we have at the moment in that solver block of Oceananigans is very much driven by what we need. So just to sort of make that a bit more concrete, this is kind of a schematic of the sorts of things the 1D implicit solver is used for. If you think of the convection example Greg was showing, we were modeling warm fluid rising explicitly. When you do the large-scale ocean things that Simone was showing, sometimes we have strong cooling at the surface, and we don't want to model all those little plumes that Greg showed. They're kind of, we just want the aggregate effect of that. So if you imagine, this is my little schematic of some surface cooling of a column of ocean. If you looked at that in the vertical and plotted, say, temperature, you'd find that you had cold water. So theta is my temperature variable here. You might have cold water overlying warmer water, which makes it kind of unstable. It means that it should have those little plumes that Greg was showing, but we don't want to kind of model that because that's something maybe is not resolving in one of these large-scale models. So mathematically, what you can do is just kind of say, okay, I'm going to approximate the behavior of this kind of mixing process on the left here by a diffusive problem, and just make the diffusion in the areas where things are unstable, where you want to mix, very large. And then that, if we tried to do this just using the operators that Simone described, things would take a long time. We'd have to do many, many small time steps. So instead, we can then formulate this essentially, and this is common in all the solvers we have, to where we're stepping forward in time, but we're actually stepping forward in time implicitly. So we end up with an equation that has some operator on the state we're looking for at time n+1 equals some function. In this case, it's just literally the state of the field at time n. So we're looking for the time n+1 state, but we have some complicated function applied to it. And typically that, has some wide stencil. So then you end up with these non-local things. So in this case, in the semi-discrete form, you end up with a tridiagonal solve over lots and lots of columns that are, each column looks like this, say, and then they're spread out over the global ocean. And so for that, we have solvers defined for problems like that. So this is an example of the tridiagonal solver we have that is used for this problem in particular. And that one, it's called a batch tridiagonal solver. So we have a generic interface solve that supports all of these implicit methods that I'll look at a couple of them. And then we specialize by dispatching on a particular type for the solvers. In this case, we are interested in something we've coded up as a batch tridiagonal solver. So that is essentially saying, we want to do a tridiagonal solve, but we want to do it over many, many grid columns all at once. So if we're on a GPU, we don't just want it doing like one column at a time. We need it to kind of be able to do all of them in parallel. These are independent solves. So I've shown a little fragment of the code of how we do this. Really, from the point of view of looking at these high-level solve things, the key point in the code, if you work with these things, is that for each of our solvers, we do ultimately end up with a function called solve with a particular signature for the type, and that those are that signature is somewhat generic, but it's you can kind of any solver we want to add to the code, we would give it. It would have to supply its own solve bang type method. And so in this case, for the tridiagonal solve, for anyone who's familiar with it, you have a kind of upper, middle, and lower triangle bit. And T is, again, another example of around the question of memory. This is some workspace. The solver has some workspace. So if you actually had a code, I think, that was doing a tridiagonal solve, that would actually add a little bit of memory to things. When we create this solver, we pre-compute some of these terms, I believe. Is that right, Greg? I'm just going to check with Greg on that. I think we pre-compute these terms, yeah?
Those can be also functions.
Okay, yeah, they could be functions, yeah.
On the fly. Also.
Okay, so it's only the workspace that actually might need to be allocated, yeah? So,
actually, we don't pre-compute them.
Yeah.
But so but
there is a workspace. I'm just trying to remember what the workspace is. Workspace is needed just then. So it's adding one array. Is that right? The workspace T is a workspace, isn't it?
That might be true.
Yeah. And so and this shows a little bit. Just I thought it'd be fun to show here, kind of how these solvers then actually look in terms of interfacing to the thing that maps things onto kernel abstractions. And I think Simone is going to show a bit more of this later, shortly. But essentially, similar to what Simone was saying with operators, in this case here, we have in the innards of this, and I'll show it in a minute, a function that iterates explicitly over the vertical index, or one index, k, but the kind of working over all the horizontal indices is again implicit. We don't actually write down a loop for that. Instead, we kind of have this syntax of saying, do this kernel over all of these XY points, and then launch these kernels using this kernel abstraction method. And that will iterate over the horizontal here. So X and Y are horizontal dimensions. And it'll do the same. If you're doing this on a CPU, it would just, kind of cycle through it sequentially if you're on a single core, or if you're doing it on a GPU, it will actually spread it out with blocks and kind of the abstractions GPUs have for subdividing their domain. So I think I'll see if I can actually leak to a bit of code with this. Let's see how it looks. So under the hood, then, what's in a solver is typically not using, it may be using the operators as building blocks, but it's got its own kind of looping structure. So I just wanted to show that. So here, we're actually explicitly kind of looping in our own code in the solver, because the algorithm requires us to do that. And that's part of its kind of difference between these local operations and the global operations. And as we were saying, the coefficients can actually be functions. And so there's some clever stuff that can go on depending on kind of whether the grid is even or stretched. And that can all be embedded in these coefficients to try and optimize how this works. So the other sorts of solvers. So I just wanted to show a little bit about the elliptic solvers we have. Let's get down. So the other family of solvers we have is a set of solvers for solving elliptic problems of this form, where you've got del squared, so d2 by dx squared plus y squared, d2 by dy squared plus d2 by dz squared. And we have 2D and 3D forms of this, plus a constant times, or a value times some phi variable. This value can be 0 in some equations, but it's kind of the general form we have solvers for, allows for a value here equals some right-hand side. And we actually have a number of solvers for that. So we have an FFT-based solver, which is the one that Greg was using in the convection example. And I'm not seeing the implicit. You were using implicit free surface, I think, were you in Simone, in the hydrostatic run. But there's a different 2D horizontal one that I think Simone may have been using in the hydrostatic run. So all of these again export a kind of solve bang interface and have their own types used to initialize them with the appropriate kind of data structures that go with the different methods. Each method can be quite different. So the family of methods, I think we've added a multigrid recently as well. So I think I did this before multigrid appeared, which was only like a day or two ago. Is at the moment in our solvers is we have a batch tridiagonal solver for these 1D problems in the vertical, and then a number of different solver options that have different numerical properties and are appropriate for different situations that solve these elliptic problems of this form. So in particular, for instance, the FFT-based Poisson solver is very, very fast, but only works for a very regular grid. And then for things where you have, say, immersed boundary conditions and other things like that, and you're on a sphere, then we use things like these preconditioned conjugate gradient solvers. So I think, given what time it is, I'm going to actually skip the hands-on bit with that. I think it's linked in the notes, but just so that we can get through the other bits of the sort of parallelism and other parts of the code. I do want to show this, just, if you're interested in kind of learning about the solvers and their interfaces, then again, you can look at the documentation online, the help stuff, by doing what Greg did in the REPL. There's also, that's all in the, the same information is in the API reference that goes with the code. So if my computer wasn't too slow, yeah, here we go. So let me just make my font maybe a bit bigger. So for each solver, we have, some documentation that describes essentially how to instantiate, create a version of that solver, and then how to apply it. So the kind of creation of a solver is quite different for each one. So if you're in a batch tridiagonal solver, then you have to pass in your lower diagonal, upper diagonal operators or functions or values. If you're using the FFT-based solver, then really there aren't many free parameters for the FFT solver, because it really only applies for a totally regular grid. So there's not much, and it really only solves one set of equations. But then there's the iterative solvers that do these elliptic problems, like a 5-diagonal iterative solver has a number of options around tolerances and preconditioner options and kind of the sorts of things you might expect for an implicit solver. And so if you're creating one of these solvers, you have to actually kind of figure out or allocate the appropriate data structures for configuring them in the right way. But then once you use them, they kind of mostly all just use this, or they use this solve interface in a quite similar way. And I think that's, so I think that was it for, maybe we'll just leap to Pigeonhole, see if we've got any more questions on Pigeonhole. I'm not sure if it refreshes. Let me just try refreshing and see. Okay, so then I think we're on to Simone. Do you want to say a little bit about, so there's an important piece to this, that everything can also run in parallel. So do you want to do it from your screen, or how do you want to do it?
I'm gonna share the screen when.
Yeah, go for it.
I'll just say a couple of things and share the screen. So I think I'm just gonna show some demonstration because it's a little bit quicker. We don't have time. So can you go back to the slides 1 second?
Oh, sorry. Yeah.
Just to say a little bit, because we have 2 different paradigms. We have as we already said, we use kernel abstractions, which is this great package to allow us to run loops on the GPU as CUDA kernels or threaded loops on the CPU. And I mean, we didn't come up with this package; we were just using it, but it gives us this great ability to abstract away the parallelization on the GPU and the CPU. And I can show quickly like how you define a kernel. You can define a kernel with a add kernel macro, and we can define just a function which adds to an array 1, let's say, and the index will be calculated directly in the kernel function. So we can just grab the index. So this index will be grabbed from the kernel through the classical thread index.x or block index definition if it's a GPU, or it's gonna be grabbed by the threaded loop or by the loop on the CPU. So it's all abstracted in kernel abstractions. You can go check that package out if you want to know a little bit more. This is just show how it works. So we already have directly the index from in this function, and now we can just add one to our array. And this is our how we define all the kernels in Oceananigans. We just have a kernel which wraps around a local operation, and if we wanna call this, we can call this this function with an architecture. In this case, I wanna run this on a GPU, so I'm just gonna give it this type which tells me run it on GPU, and then we need a work group and a work size. So if you're a little bit familiar with how CUDA works, this basically tells you if a CUDA kernel, how many threads, how many blocks you're using, and will adapt to threaded loop on a CPU. But here it's this second argument is the total size of the array I'm passing, or the total size of the loop I want to do. So 10 in I, J, and K, and this is the amount of threads per block that we're using in this case. And once we define this this function, we can just run it. So we can create, in this case, a array of zeros, and we give it our size. So we have a vector of all tens on the GPU, and then we can just run our loop function that we defined as add with a certain work group and a certain work size. We can just run it with our arguments, and this will return us an event because this function is actually is asynchronous by default, so it returns an event, and once we run it, we can just wait on the event, and whatever has happened is we have summed 1 to our X array. So it's just as simple as that. And I recommend you to check out Kernel Abstractions to see a little bit more how the innards of this parallelization works. So this is we outsourced it to Kernel Abstractions, but then we have some more coarse grain parallelization. So let me go to. We have an MPI type parallelization, which is a little bit more classical. So just multiple instruction, multiple data. We just have our, where is it? We have a distributed model, which extends basically all our methods. And the MPI depends on a multi-architecture. This multi-architecture will have inside all the information about the ranks that you have and the connectivity between your ranks. And through this connectivity, we're gonna fill the halos in our usual MPI send and receive operation. And this is using the MPI.jl module, but we just have MPI. Where are they? It's a little bit of metaprogramming here, but some I send. I don't know if it's visible. I send and I receive function, so everything is run locally except for when we need to fill the halos of the different ranks. And to handle somebody saying something. To handle global solvers, which are quite a pain because they cannot be run independently for each rank. We use pencilfft.jl, which is a great package for our FFT solver. This is actually pencilfft does the whole transpose and FFT routine. So you can imagine that we discretize our whole grid in pencils or slabs. So across the X, either the X or the Y or the X and Y direction. And pencilfft routine will transpose our data in such a way that one direction at a time will be local, perform the FFT, and then transpose in the other directions, perform the FFT, such that we have all our data transformed in the wavelength domain. Then we can perform our derivative and come back to the spatial domain. And this is all implemented through pencilfft. Now, recently, Greg has implemented a way to do FFT to do a global solve with stretch direction. So in that case, you cannot do an FFT in the stretch direction, but you have to do a tridiagonal solve. So that requires doing transposes, two transposes with an FFT. You expose the local direction where you have a vertical stretching. You solve a tridiagonal system, and then you go back in the transpose and transform back to the spatial domain. So this is our strategy for distributed memory. And at the moment, this only works on CPUs. We have no implementation of FFT on the GPU for distributed grid, because we would need to implement QFFT, but there are plans to put QFFT in pencil FFTs so that we can just dispatch to that in case of a GPU multi-GPU distributed system. Something that we have a little bit new is multi-region implementation. This is a way to have a single node, multiple device computation. So basically, if you go one slide after, Chris.
We're on your slides, but I think,
my slides.
Yeah, I think whose screen are we? It's not my screen anymore.
I think it's Greg's.
Is it Greg's screen? Okay.
Okay, wait. Let me do this. Okay, here we are. So this multi-region module actually was born because we needed a way to do more unstructured domains. So we need a way to have individual domains that are rotated one with respect to each other. So we came up with an abstraction to have independent domains, and then we figured out a way to actually allocate these on different GPUs. So this all holds on the concept of a multi-region grid. You can partition a multi-region grid in different ways and allocate the memory on different devices. So I can show a quick example here. Maybe I can run what is shown there. So let's say we define a grid. On a CPU, I already have it there. Am I using Oceananigans? But sorry, I was using kernel abstractions, so I need to do this. Unfortunately, so we can define a grid on the GPU, and then this grid is going to be defined on the device that I have on right now, which is device 0. This system actually has 4 devices that I'm running on. So it has device 0, 1, 2, and 3. Now I can take this grid that I defined on device 0, and I can split it, partition it into different devices. So this is done by defining a multi-region grid of our grid. We can choose a direction to partition it in. In this case, I'm going to partition in the direction that has 8 points. So I'm just going to define 2 partitions in the X direction, and I'm going to define on which devices I want the memory to be allocated. And this is going to be devices 0 and 1. So now I have created a region grid, which is allocated onto different devices. And with this, I can actually define a model of my. So this will create a model which has the memory allocated on device 0 and device 1. And we define a different an abstraction for loops over devices that works in kind of in the same way that kernel abstraction works for indices. So when you run a kernel, you abstract the loop over the indices, and what multi-region does is abstracts the loop over devices. So if you have a local computation, you can wrap it around a macro that is called just apply regionally, and that macro will take your function and split it into the different devices in which your memory is allocated, if you have memory allocated on different devices. And this is a way to have sorry?
Nope.
Yeah. So this is a way to have an easy way to have a multi-device system, and this is thanks mostly to CUDA.jl that has all these new advances in switching devices and copying memory asynchronously between one and another device. But it allows you to have one REPL open and have memory allocated on different devices that control the model. It's taken a while because it has to pre-compile. And to have a model which looks exactly like your normal model but runs on different devices. And so the only change that you have to do in the code is to well, this pre-compiles. Can you go up?
Yes, sure. Let me.
It's going to show how this is achieved in the code because this is taking a while to pre-compile.
Is it that one?
So, yeah, it's this one. So if you see, we have some local computations and some global computations. The only thing that we have to do is just to append this apply regionally in front of local computations, and that will, if any argument of the function there is a multi-region argument, so it is recognized by Oceananigans to be allocated on multiple devices, Oceananigans at the apply regionally will perform a loop and apply locally this function to each device. Of course, for a global computation, we have to do something different because we cannot apply a global solver regionally. This is kind of a region of research where we're struggling a bit into because having multi-device global solvers on a GPU is quite difficult. So at the moment, for the hydrostatic model, we have an implicit solver that is running on one GPU. So our global solve is gathering all the data from all the other GPUs, is performing implicit solve and scattering back the data. But for this, we probably want to have ways to do this in a more performant way in the future. And we also have plans to merge the MPI distributed and the multi-region paradigm to have some more of a unified parallelization environment, let's say. That is mostly how parallelization is done in our code.
Nice.
Mm-hmm. Yeah.
Okay.
I don't know if there are any questions.
Just before the clock runs out, I'll just say thanks to everybody for joining. And of course, you know, everything is open source, what we're doing. So we always welcome PRs. And there's a happy Oceananigans channel on Julius Lang. So, you know, if anyone wants to join, who's been on this, who hasn't joined already, feel free. Yeah. I know anything else to add, Greg, on that? Just...
I think Slack is, if you want to chat, get on Slack.
Okay, let's just see if there are any last questions. So can you provide the kernel abstraction example to GitHub? I'm sure we can. Yeah, we can put that somewhere. And I think that may be, so reload, just check. Great workshop. There you go. Oh, well, that's good. That's good to know. So, yeah, if you come back to the workshop next year, we'll be able to do something on parameter estimation, yeah? But I think we're done for this.
We'll be more mature by then, too.
Exactly, yeah. We'll have way more to go there. So, okay, so I'm gonna hit the end broadcast thing. So, bye, everybody.
Okay. Thanks, everyone.
Bye. And if you want to contribute, get in touch.
Yeah, bye.
See you.